Good morning, everyone. I'm Yingzi Wang, a PhD student from University of Science and Technology of China. I'm also an intern in Microsoft Research, and our work is about location prediction using heterogeneous mobility data. Let's start our story from this picture. Every year in South Africa, the wildebeest migrate from north to south, cross the Mara River, which forms one of the greatest migrations on the earth. Even though they are risking their lives, they get together and jump into the river without any hesitation. It is almost the instinct of animals in nature. They move regularly and conform to their community for food, water, and places. Here, regularity and conformity are the two key drivers of their migrations. Fortunately, we human beings no longer need the long-distance migration for survival nowadays, but the characteristics of regularity and conformity are kept in our daily lives. Several recent studies have shown that human movements follows the regular spatial-temporal patterns, and a very famous work on Science magazine has demonstrated that the predictability of human mobility has the upper limit of 93%. It means that most of our movements can be interpreted as regular movements. And we have some major hubs in our daily lives, like the home and workplaces, and we also have some minor hubs, like the supermarket near home and the famous restaurants near our office. We transfer among these major and minor hubs following some regular patterns. For example, the figures plot the location check-ins of two real users in Beijing, and we perform kernel density estimation to the location check-ins and obtain the bottom figures. Clearly, we can see the major and the minor hubs of these two users. It is so-called regularity. So what is the conformity? Sometimes we change our routines and visit some unfamiliar places. For example, a concert recommended by your friend, given by a very famous singer, or a new bar very popular on Yelp, on an attractive exhibition. Such irregular visits may be influenced by your friends or other people on internet with similar tastes with you. You and these people may have similar backgrounds, interests, and social statuses. It is called conformity. Our mission here is to combine the regularity and conformity to build a location prediction model. Actually, human mobility prediction is a very hot research field due to its rich applications in various domains, like the urban planning and personal digit assistant like Siri, Cortana, and Google Now. Such existing models can be categorized into two types: individual models and collaborative models. First, the historical spatial temporal patterns are the fundamental factors for inferring users' future locations. Second, different people may have similar location preferences, and so the social relationships have been brought to location prediction and recommendation systems. Although a very few methods consider both the individual and collaborative factors, like the state-of-art CEPR model. But it only focuses on one of the factors, considering the other one as side information. And these existing models suffer from some limitations. First, they fairly consider both regularity and conformity of human mobility. Second, the collaborative method of this model are all static. Second, they only use homogeneous mobility data, lack the capacity to deal with heterogeneous mobility data. So our goal here is to tackle these limitations. Given the heterogeneous mobility data, like the check-in and the trajectories of buses, taxis, which indicates the movement and the spatial temporal patterns of users. where some of these movements may be driven by regularity, and some others may be driven by conformity. Our goal is to predict the user's future locations. Let's formally introduce our model. We split the days into T time slots, considering the differences between workdays and holidays. For example, here we split the workdays into 6 time slots and split the holidays also into 6 time slots. So in total, we have 12 time slots. Then we use the U and V2 vectors to represent the M users and N venues, given us a certain time slot like the T2. Our goal here is to predict whether the user UI will visit the venue VJ in this time slot, denoted as RIJ. Denoted as RIJT. And as mentioned before, human movements can be driven by either regularity or conformity. So we here use the two terms to indicate the contributions of these two factors. The first one is RIJ. RIJRT indicates that venue VJ is a regular venue of user UI. And the second one, RJCT, indicates that venue VJ is frequently visited by the users who are similar to user UI. So the formula is like this. Let's start with the conformity term, which uses the check-in data only. Traditional matrix factorization method factorizes the matrix R into 2 low-rank matrices, U and V. Compared to the traditional one, we here at the time-changing part of user preferences, UIT, which indicates the user changeable preferences, and UI is the stationary parts which describe the unchangeable interests of user to these locations. Then we use the heterogeneous data to learn the regularity term. First, we split the city into I grids, like the vector, and map these venues into these I grids. Then we assume that venue VJ belongs to grid DKJ, and user UI travels from a grid DK to VJ. Intuitively, the probability that whether user UI will visit VJ is determined by 3 factors. The first one is the probability that user UI locates in DK now. And the second one is the transition probability from grid DK to DKJ, where the venue VJ locates in. The third one is the probability of users to visit VJ when they are in DKJ. We denote the first factor as HIK, and the H matrix is so-called hub matrix. The second factor can be estimated by a gravity model. We will introduce the model later. And the third part is can be estimated by the visit frequency of VJ in DKJ. We combine the second and third part as QJK, and the Q matrix is so-called spatial influence matrix. By now, we can rewrite the regularity term as this, the inner product of HI and QJ. Now our problem is how to learn the H and Q matrix. First, we deal with the Q matrix. We apply a so-called gravity model to learn the spatial influence among these grids using heterogeneous mobility data. And the gravity model is widely adopted in mobility analytics, especially for large population. Here, the gravity model states that the commuting flows from grid I to grid J, denoted as TIJ, is determined by OI, the number of individuals leaving grid DI, and DJ, the number of people going toward DJ, and the distance between DI and DJ through a gravity-like law. The expression is similar to gravity law. The B, A, C, and A are parameters should be learned from data. The star here represent different types of data, like bus data, checking data, and taxi data. And it is very easily intended to other types of data. Here, we achieved the optimization of this model using multivariate regression method. Then we deal with the edge matrix. As mentioned before, the human movements have hub phenomenon, and these hubs have multi-center characteristics. So the major hubs of a large population tend to form functional zones, like the residential zones and shopping zones. People transfer among these zones to engage in social economical activities. We apply an existing model to cluster the I grids into G groups. We usually are active in some of the groups, like these two, and seldom visit others, like these two. This is so-called group-wide sparsity. Even in these frequently visited groups, we are also only active in some of the grids, like the grids contains our home and workplaces. It is so-called within group sparsity. So we divide the H and Q matrix into G parts to represent the G groups. And we achieve the group-wide sparsity of the G's group by leaving the HG, or 0. Combining the regularity and conformity term, our objective function is like this. RC and H here represent the regularity, conformity, and heterogeneous. And this is the loss function of our model. And these are the regularization of our model. This part offers the group-wide sparsity, and this part offers the within-group sparsity. We achieve the optimization of our model by alternative minimization using stochastic gradient descent. So more details, please refer to our paper. Here we use the heterogeneous mobility data in our model. The first one is tracking data of Sina Weibo, which is the Chinese Twitter, and the trajectories of buses and taxis data. We only focus on the data in Beijing, China. And here are the details of our datasets. Here we compare our model with 4 baselines, MF, PMM, W cubed, and the CEPR. There are 2 matrices in the measurement. The first one is the prediction accuracy of top P, and the second one is the average percentile rank. The results of the experiments are shown here. C static and C represent the RCH model only considers the conformity term, with or without the time-changing part of user latent factor. And R is the RCH model only contains regularity term. RCHC and RCHBAC are RCH model using or not using heterogeneous mobility data in location profiles. Here, RCHC shows improvements of all the 4 baselines, which indicates the superiority of combining regularity and conformity. And RCHBAC has better performance, which indicates the superiority of heterogeneity. And workdays have better prediction accuracies than holidays. The time slot, too, of workdays has highest prediction accuracy. It is the mornings of workdays, so the highest accuracy really makes sense. Then CEPR and RCHBAC outperform PMM and W cubed apparently for unvisited venues benefit from collaborative filtering. And another interesting finding is that the accuracy of unvisited venues of CEPR and RCHBAC is higher than workdays. It might be because that the human movements to new places is more alike to each other on holidays than workdays. Last, RCH-BAC has highest APR in our models in different time slots. In summary, we integrate both the regularity and conformity of human mobility, and we provide a time-aware collaborative model. Then we incorporate heterogeneous mobility data into a prediction model and learn spatial influence and group structure based on gravity and sparse group lasso. Finally, the RCH model significantly outperforms existing approaches. Thank you.
Why do you try to do this?
Because I have told the limits of the existing models. They can't deal with the heterogeneous data. Only consider one kind of data, and we want to combine the data of different sources. That's
okay.
So with your evaluation on visited places, it seems that the results would be dominated by work and home, right? So did you do an evaluation on visited places that exclude both of those?
Both what?
Work and home. So it's very easy to do prediction during the work week based on those two places, right?
Yep, but we combine the considering of regularity and conformity. The home and work may be regular places of people, right? But we often visit some unfamiliar places. And these places should be learned through the conformity term. Thank you. It's a very good question.
So in evaluation, you didn't separate the two terms, right? I mean, evaluation on some kind of data, like the work and home and unfamiliar places. Do you have that kind of a separation?
Yeah.
Any other questions? Next time, the speaker again.
Thank you.